Okay, so we're back here. Hopefully your break was good, and we're gonna get right back into chapter 5 now. So we're gonna start with that, and this is all your quiz and your homework is this week is just this one section in chapter 5. It's the opening section. There's a lot to it, but it's definitely something that we need to make sure we take our time and go over and cover all the bases here. So I'm gonna jump right into this, our PowerPoint here. And show you what I'm talking about here. So, antiderivative integrals, first off, if you heard that, they're the same thing. They're identical in what you have here. Um, sorry. Okay, go back here. I was trying to turn on a setting here and it didn't work here. Just give me a second. Okay, sorry about that delay there. Basically, if you've heard integrals before, which you might have, it's one of the core pieces of calculus. They are the same as what we're going to be learning as antiderivatives. So basically, an antiderivative is just as you thought. It's the backwards of what you've been learning on derivatives. How to find a derivative, we're going to do exactly everything backwards. So basically, they're saying we have a function f, capital F. It's considered an antiderivative of the function little f if basically you take the derivative of it and you get right back to the function. So it's like I said, just think of it as you're going exactly backwards everything you've had before. So example here, we have this function f of capital F of x equals x to the fourth over 4. It's an antiderivative of x cubed because when you take the derivative of this one, x fourth over 4 becomes an x cubed. That gets you this function. It's kind of like going backwards and saying, what's the square root of 25? Well, the question is, what number do you square to make 25? Oh, the answer is 5. Here, when they say an antiderivative, it's basically, an antiderivative of a function is, what can you have where you take the derivative of it and you get right back to the original function? That's considered the antiderivative. And that's what we're going to do this entire chapter here. So, example here, and they notice there's a few functions. X to the fourth, if you take the derivative of it, you get x to the third. That's our key. What gives you x to the third? Well, you see this other function here, x to the fourth over 4 minus 3, and you'll notice when you take the derivative of this, you also get x to the third. Or they throw out some weird one over here, x to the fourth over 4 plus e to the pi. Again, that's a constant. You take the derivative of any constant, it goes away. So what they're saying is there's a lot of potential antiderivatives for one function because you can just add any number you want. And again, taking the derivative of any number gives you a 0. So it doesn't really matter what this other number is, whether there's no number like this one, or there's a -3, or there's this e to the pi. Any other constant, it doesn't matter. It's what the variable is. Because you take a derivative of a variable, that's what you need to get this x cubed. That's what we're looking for here. So you're going to see this notation, this capital C a lot, is saying that as long as you have the x to the fourth over 4 in your antiderivative, this plus C means any number can be there for C. C could be a 1, it could be a 2, it could be a 9, it could be a -75, whatever it is. Because when you take the derivative of this, the derivative of x fourth over 4 is an x cubed. And no matter what constant you want that c to be, when you take the derivative of that, you're getting a 0. This is what matters. Do you get the x third? So a lot of times when you find the antiderivative, or you'll see in a minute, we'll do the integral, they always put this plus c on here, and that's just a safe space to show you that there are multiple answers. We don't know what that c is, and it really doesn't matter, because it's going to go away when you test it backwards. So again, it's kind of a repeat right here. It's saying the same thing. It doesn't matter what the c is. Anti-differentiation of a given function does not give a unique function. Okay, so the antiderivative is what they're saying, this big word right here. It just means there's a lot of different answers, but every one of them, they will give you, if you take the derivative, you'll get back to the original function, the main one that you have here. Okay? So, let me pause here and moving on. Okay, so if the derivative of the two functions are equal on an open interval, then the functions differ at most by a constant. You'll see it Don't worry about this theorem. It really isn't going to matter too much. I'll show you a picture in a bit, and you can kind of see, yeah, you'll see what they mean by this differing by a constant. So don't wrap up on that too much here. And I'm going to just get right into the problems, things that we can see here. So they're going to remind you of something. Notice that if you take the derivative of x squared over 2, you get an x, okay? So they want us to find all the antiderivatives of this. Well, what that means is we know we're looking for something that if you take a derivative of it, you get an x. Well, we already learned that right here. We already proved that a second ago. Essentially, when they say find all the antiderivatives, that means x squared over 2 will work, x squared over 2 plus 1, x squared over 2 plus 2, x squared over 2 plus 10, whatever. Those are all the antiderivatives. So basically, we're looking for a few things. I'll talk about part B in a second, but what it's saying is this extra k, or they used the c earlier, that's what they're talking about when they mean find all of them. Any one of them, it doesn't matter what it is, as long as it has some little capital C is what's normally used. Sometimes you'll see a little k for other reasons, but that's all it is when they say find all the antiderivatives. It's not just the backwards derivative, it's also accounting for that plus c, or in this case, the plus k. Now, in part B, they're saying graph the antiderivative of f that contains the point 0, 0, the point 0, 1, and the point 0, 2. Now, I'll talk about exactly what that means. First, here is the formula for the antiderivative of this problem. F of x equals x squared over 2 plus k. And remember, k could be anything. So they want us to find the graphs that have 0, 0, 0, 1, and 0, 2. So here's what we're talking about. All right? Here's that formula right here. What they're saying is when you plug in 0, 0, 0 and, for x, you're also going to get that for y. Okay? Now, kind of the way they work this out isn't exactly the best, but here's what it is. All of our points have to have, all of our graphs have to have a point 0 something, 0, 0, 0, 1, 0, 2. So here's what I'll show you. Remember the antiderivative formula that we just got was this. Okay, now that k is unknown. Remember, there's so many different things it can be. But let's start with this one, this 0, 0. We're going to replace this with 0 because that's our y, that right there. And we're going to replace x with 0. Oops, sorry, go back. X with 0 right here. And what I'm basically doing is I'm going to solve for k. And I get k is 0. Okay, I know that doesn't mean a lot to you, but what it's saying is this particular point right here will have the equation f of x equals x squared over 2 plus 0, the 0 that we just found. Okay, now I'm going to do the same thing with the other point. You'll see where I'm going on this one, and that's how they're getting that next line. Now I'm going to plug in the point 0, 1. So my y value is 1, my x is 0. And when I solve for k, you kind of see that first term just cancels. And we get 1 equals k. So that means for this point, I'm going to go right down here, we have the function f of x equals x squared over 2. The plus k, in this case, the k is 1. And for the last one, we have that function right there. Basically, whatever the y value is, that's going to be the k. So that's how we're solving for the k. The k can be anything. If they give you more information, like they give you a point, you can go find the k value or the capital C value that we're going to deal with later on. Until they give you that, we have to leave our equations, our functions, in the generic form right up here on the top right. The one thing I'm not erasing up on the top right. That's the generic form, the form that we don't know. If you really need to find that k, you need to be given more information, like give me a point, give me something. So just treat this like 3 different problems. If I was to plug in this point to this function, this will allow me to solve for the k, and then I can make the exact equation, that one right there. Okay, so that's kind of the math, the steps that they didn't show here, how they got this second line. But they want us to basically graph each of these. So you'll see the 3 graphs are basically going to be all 3 of these. And that goes back to that theorem I was saying earlier, where when you have a family of antiderivatives, they're all going to be off by a constant. Whatever it is, that's the constant, but it's essentially the same shape. And every one of these graphs If you took the derivative of it, it would be, I can write this, the derivative is going to be f of x equals x. It doesn't matter if you take the derivative of this one, or this one. All three of them, that's our derivative down there. And that's the key when you're finding the antiderivative, or in a few minutes, the integral. You just want to make sure that everything that you find gives you that same derivative, that same result for the derivative. Okay, so how are they related? Well, we talked about that. They call it vertical translations. They're just shifts of each other. They just move up and they move down, but they're the same general shape. That's what you need to see. Okay, now we get to what really matters here, this indefinite integral. This is the integral sign. Looks like a music note, or a music symbol right there. That sign means take the integral. The integral is, for our purposes, it is the antiderivative, all right? So if you have to find an integral of a function, the key right here, this dx, remember the dy dx stuff we did? That right there is the key. That tells you we're dealing with the variable x, so you're going to take the antiderivative, or in this case, the integral of whatever that function is. You're going to do it with respect to x, and what you're looking for is, I'm looking for something, some function that if I was to take the derivative of it, let's just say we get an answer. Whatever our answer is, if I was to take the derivative of it, I would get right back to that original function right there. So that's what we're doing. We're going to be going exactly backwards of all of the derivatives we did. And the check is, well, take the derivative of your answer. If it brings you right back to where you started, then you did this correctly. Okay, so there's your integral sign. Whatever the function is that you're working on, that's called the integrand. Not so much important, the definitions, is just how to do it. The dx is what matters, whatever that d is, because in some problems you're going to see dx, dy, dz, dd, whatever the case, that's the letter that you're going to be working on, that you're going to be dealing with. All right, so a couple examples. You see here, we're going to take the integral of x squared. So we're looking for something, some answer, such that, remember, if you take the derivative, you go right back to where you started. So they give us the answer right here, okay? And they show you the reason is because if you take the derivative of that, you get x squared. All right, now that's only going to get you so far, showing, watching someone else do the work. You're going to see some formulas. These are just examples showing you why they're true. I know the question you all have is, well, how do I get to it? How do I know it's x cubed over 3, etc.? Now, what this really is, this part, they just want to show you a comparison. These are all the same function, something squared. They're different letters, though, okay? And I'm going to point out something real quick. Oh, give me a second. Okay. Apologies. There is a little tiny error. If I can fix this. All right, not going to let me do it. That's supposed to be what do you call it? A U right there. They're supposed to be the same letter. So skip that. Don't like you've seen. Sometimes you got some errors here, but that's supposed to be a U on that last one. I'm just going to write over it right now just to kind of show you what I'm talking about here. Okay, that right there is supposed to be a U. Now, what I'm trying to point out, my whole goal here was to show you that when you take the derivative of x squared, this is the instruction. It's like referring to x. This is the t square function, so it's a t. This is a u square, so it's a u. So it's saying that's the variable. They're indicating this is the variable of the problem. This is what you got to work on. So in every case, if you were to take our answers, which are the same, every one of these, if you take the derivative of those, you get right back to where you started. Here and there. All right? Every time you do an integral, or at least for these first ones, you don't just tell me the x cubed over 3 or the t cubed over 3. Every one of them, notice, has that plus c. That's a crucial, important part. And I'll tell you right now, if you don't put that plus c, you're going to get it marked wrong in MyMathLab. So make sure that part is there. Okay? So let's go on to next part. Okay. So They're basically the same thing, or sorry, integration and differentiation, they're just going backwards. They're like multiplication and division, addition and subtraction, square rooting and squaring, they're backwards. So for the most part, if you took a derivative of an integral, they're going to cancel right off and you're going to be left with the f of x. Or if you took the integral of a derivative, you're going to be left with the same thing. And you'll find that very quickly. You're not usually going to do both of them. They're going to make you do one or the other. But just give you some ideas. So this is where we're going to start with what matters. Okay, so if you remember, let me give you an old example. If I was to take the derivative of x to the fifth, you all remember the rule. You bring the power up front and you subtract 1 from the power. Remember that? That's why we get the 5x fourth. Derivatives. Integrals, on the other hand, it's essentially the same backwards notion. Instead of subtracting 1 from the power, we add 1 to the power. And instead of dividing or multiplying by the 5, we divide by the new power. So that's your process. If you had the integral of x to the ninth, the process is add 1 to the power, divide by that new number, and then I can't show you that, but put the plus c. That's your integral. That's your antiderivative right there. That's all that matters. The one caveat is this is not going to work if your power is a -1. It'll work for any other power, fractions, decimals, negatives. But remember, if it's a -1, it's not going to work, and I'll tell you why. Because if you add 1 to this power, you get a 0, and you can't divide by the new power. That's why there's one flaw right there. It won't work when x is, if the power, the n is a -1. Any other power, it's going to work. I'll give you one more example here on the left side. Like I said, it does not matter what power you have, as long as it's not a -1, you can find the integral of anything. So let's go with x to the -2. Well, answer's the same. Add 1 to that power. Okay, -2 plus 1, and I'm just going to save a step here, that's -1, and you divide by the power. I'll rewrite this as -1 over x, and don't forget to add that plus c. There's your integral. All right, so whether it's a decimal, it'll even work with 0, you'll see in a second, that'll work the same. It'll work with negatives, it'll work with fractions, it'll work with decimals, any power except for -1. So let's say we had the square root of x, and we're going to find the integral of that. Well, kind of like we did in the derivatives, I want to make that a power that I can work with. So rewrite that. It's still the integral, but it's now x to the 1/2, and now we do the same rule. Add 1 to the 1/2. That gives me 3/2. Divide by the 3/2, and there's our answer. And I can clean that up a little bit. I can call it 2/3 x to the, 2/3, 3/2 power. Just so that you don't have a fraction on the bottom. But there's your answer right there. Okay, it's going to work for anything. So, when you have a single power, rest assured, it's going to work for every single one of those things that you have. Okay, so let me erase this. Now, a couple other ones. If you go back. Okay, if you have an integral of e to the x, remember the derivative of e to the x was e to the x? So the integral of e to the x is also e to the x. Same thing, the easiest one you have. Again, add the c to it. If you have x to the -1, remember the one number that didn't work here for the first property? Well, remember, x to the -1 is 1 over x, and you learned that before. The integral of that is natural log of x. Excuse me. Just like the derivative of natural log x is 1 over x. So that's your one exception, your one fix. Constants, if you have a constant, you can just pull the constant out in front of the integral and multiply to your answer. You don't need to have that. Okay. Any other time, if you're adding two functions, you can do it as two separate integrals. You don't have to, but you're welcome to. Okay, just like derivatives, if you have a polynomial, how you take the derivative of each piece one at a time, you do the same thing. You can do the same thing for an integral as well. Okay, so a couple things. They're going to go over some properties. We don't even have to do this, but I'll show you. if you have a constant, so I kind of go backwards on some of these just to kind of refresh your memory. Remember, when you take the derivative of something like 7x, remember the derivative is just plain 7. Well, when you go the other way, the integral, so this gives you the derivative. If you take the integral, you basically just add 1 to it. Now, if this doesn't really work out for you, I'm trying to show you how a way I can look at this is the same as x to the 0. Okay, when you have a constant, it's like an x to the 0. It's like it's not there at all. So that's one of your choices here. You can do that and then follow our new rule, add 1 to the power, divide by that new one, and that's how they get the 7x plus c. Okay, that's all that was right there. Nothing, there's no fancy steps. Just remember, if you have just a constant and you're told to take the integral of it, all you have to do is just stick an x there and you're done. Okay, so let's get rid of that. And a lot of these on this page are just kind of examples. Here we have, and let me go back. On this one, notice I just said you stick the letter there if you have a constant. So if you have, 25 dx, the answer is simply 25x plus c. But I'll give you another example. If you had something like that, remember, this is the instruction. It means we're dealing with a variable t. So the answer to this one is not a 7x. It's going to be a 7t. It's whatever letter that is with the d. That's the letter that you rise up in the power. That's what you add, you bring to the table. Most of the time, you're already going to have that letter there. The exception is here, like when you have a constant, you just have to put that extra piece there. You have to follow the instruction of what letter are you working on? Is it dx? Is it dy? Is it dt? That's what you put on there. Okay, so on this case, they took the 4 out front. You didn't have to, just to go figure out that we're going to take the integral of e to the t dt, and the integral of e to the t is simply e to the t. Once again, you add the c to it. Here in this case, you can pull the 3 out, or you can leave it. It's going to work the same way. The rule when you integrate an x to the 6th is you add 1 to the power, like this 7 right here, and then you divide by the new power. That's how we get 3/7 x to the 7 plus c. And remember, if you're not sure, you always have the ability, let's take the derivative of this. Well, that's 7 times 3/7 x to the 6th. The constant, the derivative of that goes away. And now I get a 3x to the 6th. That was what I started with. That's the way you can sort of verify that you did in fact have the correct answer is when you take an integral, if you're not sure, take the derivative of that answer, and that'll prove to you that it was the right one. Okay, so another one here, when you have multiple terms, you don't have to do this, but it's an option. You can just make it as 3 separate integrals, and the integral of this, add 1 to they pulled the 2 out, and they pulled the 3 out, and they pulled the 4 out. Either way, you can leave them or pull them out. And then the integral of x to the 3rd is x 4th over 4. The integral of x is x squared over 2. And remember, what we're doing every time is we're adding 1 to the power, make it a 4, and divide by the new power. Add 1 to the power. It was a power of 1, now it's a power of 2, divide by the new power. Here, there is no x, so remember the rule. You just put an x there and you're done. And then, of course, add the c. And then the last step is cleaning it up a little bit. Like always, we've got to do a little bit of algebra, a little bit of cleanup just to get your answer right. This case, we have a combination of the two. So they broke this up into 2 pieces, pulled the 3 out, and remember, the integral of e to the x is simply e to the x. The integral of 1 over x is natural log of x. And you do have to put that x in an absolute value. It won't matter so much today. It'll matter in our subsequent sections, but for now, that's all we have to do. Okay, here's another one. Like, as these problems get more advanced, you have to clean it up a little bit. They pulled the 5 out, and then they rewrote this. Instead of 1 over x to the 4th, it's x to the negative 4, and then we integrate. We follow the rule, which was add 1 to the power. Well, my power is negative 4. When I add 1 to it, I'm going to get a negative 3, and that's the number I divide by over here. So you see, new power, add 1. We subtracted 1 when we did derivatives. When we do integrals, we're adding 1. and we are dividing by whatever the new power is, in this case, -3. Okay, and then you see what they did here is they left the -5/3. This x -3, we brought it to the bottom, so it's a +3 power down here. Still a negative, though, in front of the problem. Okay, here, don't forget what the definition of this is. They'll pull the 4 out, and then the definition, when you have a root, it's a denominator power. When you have a regular power, it goes as the numerator. So this cube root of t squared is t to the 2/3. And we do the same thing. We add 1 to the power, and we divide by that power. And if you need to go off to the side, and if you need to show this, this is not a bad thing. I don't know how to do 2/3 plus 1. Well, yeah, I got to get the common denominator. And then I combine those. And this is how they got that 5/3 right there. And then, of course, we divide by the 5/3. That's how they end up with where we are right now, at least. Okay? Then clean this up a little bit. This 5/3 that was divided by is the same as multiplying by 3/5. And then the 4 times 3 is where they get the 12 from, and that's where they get 12/5 t to the 5/3. And once again, don't forget about that plus c. This is your entire answer right here. Okay? So, like I said, a lot of these slides are just sort of going over some examples. In this last problem, or this next one, I should say, we have x to the 4th minus 2 over x squared. In that particular one, the trick is if you have one term, this only works when you have one term on the bottom, you can split this into 2 fractions like that. And then you use your algebra. We have not integrated yet. It's still an integration symbol there. We clean this up a little bit, and that first term becomes x squared. The second term becomes 2 over x squared, which becomes 2x to the -2. And now we do these two integrals and kind of look at what we get. Make sure you know where these came from. Okay, so notice this integration symbol and this dx, this sticks around all the way until the moment you do the integral. Like as soon as I add 1 to the power and divide by that new power, now there's no more integral. No more integration symbol, no more dx. I have an answer right there. And then same one at the second part. I added 1 to the -2. That's how I have a -1 power. I divide by the new power. And all that's left is just clean this up a little bit, tidy it up. We get x to the 3rd over 3 plus 2 over x. And once again, always make sure you have that plus c. Okay? And next one here, we have a couple things. And you see that they're just making it a little bit more complicated, but the rule is very simple. Don't get tripped up when you see these weird powers or these weird problems. Okay? These are 2 separate terms. So you treat them individually, just like if you were to take the derivative of these, you treat them individually. Let's rewrite them both as actual powers. So when there's a cube root of x on the bottom, that's a -1/3 power. A square root is a 1/2 power, and now we integrate. When I add 1 to the -1/3, this is what we're doing. You add 1 to the 1/2 and divide by the new powers. And like I said, if you have to go off to the side to figure this out, feel free to do that. As time goes on, you're going to get these fractions very good, and you're going to do them in your head. But for now, do not be afraid to show the work. This is how they got the 2/3. And then, of course, they divide by 2/3. On the other side, we have 1/2 plus 1. Hopefully that's not as bad for you. That gives you your 3/2, and you divide by the 3/2. Then we clean it up, and remember, dividing by 2/3 is the same as multiplying by the reciprocal. So what they did was they had this 2/3, I'm sorry, we multiply by 3/2, so the 2's cancel off and we have just the 3. Over here, we take 6, we multiply it by 2/3. That's how they got the 4 right there. Okay, so there's some basic math, some algebra, lots of fractions are going to be in this integration chapter. I can tell you that right now. And they're not going to be ugly fractions. They're going to be things just like I'm doing here. Thirds and halves, maybe a few fourths and fifths, but for the most part, it's going to be just a couple of basic fractions, making sure you know how to do the process. Okay, so I'm not going to do these last couple slides. We don't need to worry about these at this time. I'm going to skip around a little bit, but I want to just get to the homework problems to show you what matters here, what we're doing. So let me pull up the homework. Here we are. Hopefully you're up to date. You've tried some of these by this time. Um, and if you're getting stuck, hopefully this video will get you back on track here. So look at what we have. All right, we've gone a long way here. Homework number 13, 5.1. Just show you a few of these here just to make sure we're all in agreement and we all know what's happened. Okay, so first problem, we're going to find the integral of 3. Well, remember the rule. If you have a number, all you do is you just add, I won't say add, you multiply by the number that was, the variable that was there. So if I'm integrating 7 dx, it's 7x. If I'm integrating 3 dx, it's simply 3x. And, what did I miss? Evaluate it. Oh, you guys see what I missed? Thing I've been hounding you to do 100 times? Don't forget your plus c. That's why I got it wrong. So that's a good lesson. If I got it wrong, you're going to get it wrong every time. If you're wondering why, first question, ask yourself, write this in your notes, write this on a sticky note by your computer, your laptop, your tablet. Did you put the plus c? Every time, make sure that plus c is there. Okay, let's move on, do a couple more of these. And you see, there wasn't any writing on that one. It's just a matter of seeing it and knowing the answer. Here, show you what we have here. We have the integral of x to the negative 10 dx. Well, all I'm going to do is I'm going to add 1 to the power. That gives me a negative 9. Divide by the new power and put the plus c. And then if you want to, they may add, this is the answer right here, by the way. Okay, sometimes you're going to see them say, well, no, we don't want you to have the negative power, so they're going to have you move the 9 down to the bottom, and you can have this one right here. Now I'm going to plug in the first one. Let's just kind of use me as a guinea pig to see if this works. But if I said x to the power of negative 9 over negative 9, just as I had it, the first step, see if that works. And it should work, and it does. And if you would have put the simplified one in there, that would have worked just the same. So they're both legitimate answers. It's just which one, and in the beginning, don't overthink them. Try them out. They're going to work. It's that plus C that you got to worry about the most. That's the big one that you're going to get doctored. You're going to basically get marked wrong if you forget to do the plus C. So make sure you have that plus C. I can't say that enough, and hopefully my mistake on the first one will prove it right. Okay, so if n is an integer, then x to the n plus 1 over n plus 1, notice that's the formula, that's an antiderivative of x to the n. So that's the basic formula right there. And they want you to basically discuss the validity. Look at your 4 choices and you can see it. Let me zoom in a little bit. I know this is a little bit small. Okay, I'll lose a little bit of my writing space, but this will let us see it. Notice there is an exception. Remember we talked about this. It won't happen when that power is a negative 1. It's going to work everywhere else, but not that one right there. And that's all this question is doing, is it's just getting you to recall, oh yeah, I can't have it for that. That's all they want about that one. So there's nothing that you have to work out, nothing special on that one. It's just make sure you recall you don't do that when it's a negative 1. We have a whole other formula for that one. Okay, let's look at number 15 here. Evaluate the following integral. All right, now we start getting into the problems that matter here. Okay, so I'll write an extra step. You don't have to do this, but remember that's a 1/2, which I can rewrite to be 8x to the negative 1/2. Notice these first 3 things I've written, they're all the same exact thing. I haven't done the integral. I have just rewritten the original problem. That's why the integration and the dx is still there. Now I'm going to do the integral, and you see we add 1 to the power. So when you add, and I'll just kind of write it up here to the left, or the right, I'm sorry. If you add 1 to 1/2, you get a positive 1/2. That's my new power, and I divide by the new power. Okay? Put the plus C. So remember, a lot of people see this and they want to write a 4. Okay? Not a 4, because it's not 8 times 1/2. It's 8 divided by 1/2, which means I'm essentially multiplying by the reciprocal of that. It's like multiplying by 2 over 1. And you'll be able to do more and more of this in your head, so don't worry. There's my answer right here. Or 16 squared of x plus c. Both of those are good. Okay, and I'll try to enter that second one right there. Let's do the square root down here with my little palette. And again, I'll purposely not enter it with the plus c just to show you. It's incorrect. And they don't give you that hint there. You know, it kind of implies like you got something wrong. Now let's always try to put that plus c. Notice that's all it took. That's all that was wrong with that problem. So make sure you're aware of that. Okay, let's jump to number 19. Okay, so on this one, we have 5x to the fourth minus 4 over x to the fourth dx. And this is not too much different than the last one. The main thing is, and you're going to see this a lot, and I might have said this a few times, calculus stuff isn't hard. This integral stuff is not hard because all you're doing is you're adding 1 to the power and dividing by the new power. The hard part is going to be the preliminary, the before and the after, like the part I'm erasing, where you're using your old rules of algebra to try to get it to look like the right integral, you know, the thing that you can integrate, and then to take your answer and to clean it up a little bit. That's what you want to do. That's where the work is going to come into play. So here's my problem. Just rewriting it right here. All right. So now I'm going to go one at a time. And before I do that, though, let me just do a little rewrite. Let's make this what it is. X to the negative fourth for that second term. Now I can integrate each one. All right. So when I integrate this first one, the 5 stays there. The x increase the power by 1 and divide by the new power. On the other one, increase, excuse me, increase the power by 1. And remember, when you take negative 4 and you add 1 to it, you're getting a negative 3. So now I just clean this up a little bit more. We have x to the fifth plus a 4/3 x to the negative third. And then if you want, you do not have to do this. You could bring that down, the negative power. That one's good. That one's going to be good. I don't think this one will work because they want you to clean up the, simplify any fractions you can. But I'll just enter that top one. X to the fifth plus 4/3 x to the negative 3 plus c. I hope I typed that in right. Yep, and there we go. Okay, so pause that if you need to look at it a little bit longer, and then resume. We'll go on to the next problem here. Okay, so on this one, they give you some information, and what we're doing is we're going backwards of a backwards step. You know, antiderivative integral is going backwards. We're doing kind of the same thing, but twice here. So what they're telling you is, remember, that was a derivative. They tell you the derivative is this right here, the derivative of some function. What we need to find is what's the original, the thing that we take the derivative of to get to this right here. We want to know what that original function is. So how do we do that? Well, we're going to integrate. If we integrate, we should be getting the original. So that's what's going to happen right here. That's the process that I'm going to take to get this y. Now, I don't have to write all the integration stuff, but I will in this particular case. To get the y, the original function, I'm going to integrate what they just gave me. And that's going to go dx with respect to x. Okay, so what do? I'll follow the rules. Add 1 to the power, it becomes a negative 4. Divide by the negative 4. Over here on the second term, we add 1 to the power. That's not going to work. Remember that rule? Wait a minute, I can't get a 0. Remember what the rule was? Okay, so I'm going to clean up the last step just to show you. And I did this on purpose because sometimes you're going to fall into that step where it's like, wait a minute, why is that not working? Remember, it doesn't work when it's a negative 1 power. You got to think of it, that's 5x. Oh yeah, I know what that rule is. Remember, it's the natural log of that x that we just found. Okay, so far? Hopefully. So now, we have the original function. Now, I'm going to clean this up a little bit more. It's 3 over 4x to the 4th plus 5 natural log of x plus c. That's my original function, but this is a case where they want you to find the one that satisfies the given condition, that part right there. If they just said, give me the antiderivative or the integral, we have an answer down here. We've done it. But they want the one. Remember what that meant was too, with that c, there's a whole family of them. That c could be 1, 2, 3, 4, 5, 10, negative, whatever. That's the general form. They want a specific one that satisfies this. It means if you plug in 1 for x and 5 for y, it's going to make this true. So what I have to do is what I was showing you earlier in the PowerPoint. I want to replace everything with that 1 comma 5. So you see this over here? This means x equals 1, y equals 5. I'm going to plug them into the function that I just found here that I have boxed up. So you notice I put a 5 for the y. I put a 1 here for this x. I put a 1 here for this x. And I have that plus c. Now, I hope you remember what the natural log of 1 is. Pause. Think about it for a second if you're not sure. And hopefully you remember the natural log of 1 is a big 0. So basically, 5 plus 3/4 equals the c. And I could call it 5 and 3/4, but remember in algebra, calc, we don't really want to do the mixed numbers. They want us to do these improper fractions. But regardless, we have found what c is equal to. So when you get this box right here, you get a general form. By plugging in a specific point, you'll be able to find the exact equation you want. Basically, you can find that c value, the c value that makes this true. We solved and got the c, so I'm going to plug that in right here. I'm going to replace that c. So my new answer is going to be all of what's in that box, but no plus c. It's going to be the 23/4. So minus 3/4 x to the 4th. All right, plus 5 natural log of x, and make sure you have that absolute value symbol, plus 23/4. Okay? Instead of the plus c, this is what this problem requires. It requires you to do an extra step. And let me look, make sure I didn't miss something here. All right, everything looked good. Let me check my work one more time here. Okay, so there's one tiny error I messed up on in trying to write this. Now I see it. The original problem was all this. I forgot to put that little -1 right there. See that one right there? I completely overlooked that. And that's important because when I do the integral of it, let me try to squeeze it in here. The integral of -1, remember, is a negative x. No more dx, plus c. So I'm missing an entire term. There should be a minus x plus c. So that's going to change a lot of what I got here on the left. So let me just start this right side. Let me just start this over, the part where I'm solving for c. So now the answer in the box is the correct integral. -3/4 with an x to the 4th on the bottom, plus 5 natural log x minus x plus c. So we'll see how this turns out. I'm going to do the same thing I did a minute ago. I'm going to replace the y with a 5, and every x is going to get replaced with a 1. So that's a -3/4. We get 5 natural log of 1. We get a -1 and we get a plus c. And remember, this whole thing becomes a 0, so that's gone. So we get 5 equals -3/4 -1 plus c. That becomes 6 plus 3/4 on the left. And now we get 27/4. So a couple things were off. All right. The -3/4 x to the fourth was good. The 5 natural log x was good. I need to put this minus x in here, and this should be a 27/4. And then we can check that out and see if it works. And I'm looking good there. Okay, so in other times you miss a term like that, it's always bad. In an integral, it's really bad because when you miss this -1, because powers go up when you integrate. Remember, you're adding 1 to the power. That's an entire x here that I neglected. So now we have it, and there's our answer. So step 1, find the integral of that. We got it. And then step 2, solve by plugging in these values, solve for the c. And so when you submit your answer, it's the integral, but instead of a plus c, it's some number that you figured out. Okay, so once again, pause that if you need to, look at it some more, and then resume, and we'll move on. Let's look at number 27. Okay, so here's one of these. We had the same example earlier, or one like that in the PowerPoint. We'll just kind of go over that. So this is x to the 7th minus 3x over x to the 6th dx. So the first step, I'm not going to do an integral. I'm going to rewrite this as 2 separate fractions. And the reason I can do that is, remember, as long as you have one term on the bottom, you can do the split. You can rewrite this. So this actually makes the problem pretty good. That whole first term just becomes an x. So now we're looking at x minus 3x to the -5th dx. And we just have to find the integral. Now you notice this word indefinite, I didn't really talk about that. When they say an indefinite integral, for now, it's just an integral. Later on, we're going to have things called definite integrals where we're going to be plugging in points for x to figure out actual numbers. When that happens, you'll see definite integral, and this will be, you'll see the difference of the two. For now, an indefinite integral is just an integral for you guys. Don't overthink, don't get scared when you see that. Okay, so now remember, all these things I've written on the screen right now, we're just rewriting the integral. Now we do the actual integration. So remember, up your power by 1, divide by the new power. Over here, up the power by 1, -5 plus 1 is a -4, and divide by the new power, and then do the plus c. So I've done the integration. Now I'm just going to clean up a little bit. That should be a 3/4x to the 4th. And remember, you can make it x to the 4th on the bottom, or you can leave that x -4 on top. Either one is going to be sufficient when you're plugging in your answer. Don't worry about that. So we have x to the 2nd over 2 plus 3/4 and x to the +4 on the bottom, and the plus c, and that one is correct. So again, pause if you need to see this a little more. If you're good, resume, and we'll move on to number 31, if there is a 31. I think there was. Okay, so in this one, assuming that x, and I didn't mean to fill this in, I was looking at it earlier. Let's see if I can try it. Yeah. So they're telling you x is greater than 0. Use differentiation to justify that this is true. Well, really in this case, I'm going to tell you this is nothing unique. You know this formula. We already went over this. The integral of 1/x is the natural log of x. And then what they're saying is if you were to take the derivative of this answer. So notice what they're taking the derivative of is the answer we just found. We're going to get right back to where we were and get just that 1/x. That's all that they're saying. They're just kind of confirming that you know that when you take an integral, then you take a derivative, you get right back to where you started. Okay? The derivative of natural log of x is 1/x. The derivative of a constant, remember, is always going to be 0. So that's all you need to fill in on this number 31. These two parts, it looks uglier than it is, but that's all that it is. So I think that's it for that one. Let me close that real quick. Yeah. So try these out. You should be good to go on the word problem. if you see one like we just had, don't worry too much about it. If you don't get it on the first crack, you'll see how it is. All they want you to do is, again, find the derivative, the integral, and then if you have to plug something in, you do. Main thing I just want you to get is the practice of how to do the integration. The main thing is upping that power by 1, dividing by the new power. You see how many times we did it in this example. Just keep doing that, and you'll see what happens. Okay? So I'll stop it here on this one. If you have any questions, like always, shoot me an email. And this is it for this week, this one section. So your quiz on Monday next week is everything that we just had. You know, everything on this section, that's it. There's no 2 sections. It's all from this one section. So work on that. And like I said, shoot me any questions you have, and I will record a couple more videos for next week, and you'll see that soon. Have a good one.